Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Niccolo Somaschi, CEO of Quandela. Niccolo describes the company's approach to quantum computing, emphasizing the use of photonics and semiconductor technologies to manipulate photonic qubits. He highlights Quandela's focus on building commercially useful quantum computers, the development of a unique programming framework for transforming gate-based circuits into photonic operations, the deployment of their 6-qubit processor, the challenges for scaling photonic quantum computers, and much more. We hope you enjoyed this episode. Hello, Niccolo, and thank you for joining me today.
Hello, Yuval.
So who are you and what do you do?
I'm the CEO of Quandela, a quantum computing company based in Europe, co-founded in 2017 in France by myself and my collaborator Valerian Gies and Pascal Senelard, who is a professor at the Research Institute C2N, Center of Nanoscience and Nanotechnology, part of the National Research Center. And Quandela builds quantum computers with increasing power, searching and following the quest of building useful, commercially useful quantum computer through error correction.
And what is the underlying technology?
Quandela exploits photonics and semiconductors. So we manipulate photonic qubits, which are generated through semiconductor nanostructures, semiconductor devices, which also serves as qubit itself. So it's a photonic quantum computer, but also manages matter-based qubits, which is a bit of exotic approach.
How does one program a photonic quantum computer?
Well, photons serves as a very efficient qubits because they allow different kinds of encoding. They can be encoded in so-called URL using integrated photonic circuits and waveguides. And that's the main approach. But it also allows to use time being, which in combination with photon integrated circuits permits to develop processors which are interconnected, where part of the computation and manipulation occurs in circuits, in processor, and parts it transfer through fiber loops that basically acts as memory in the logic sense of the computing part, and interconnects to other ones. So it allows to expand, distribute the computation, and overcome some of the issues, space basically, which affect several platforms manipulating matter-based qubits.
So that probably means I can't just take a CASM program and send it to your computer, right? I have to do something else. So what, if that's true, what kind of applications or what kind of programs can I run on the computer?
It's also true what you're saying. Indeed, photons allows an encoding which is purely photonic. We heard about boson sampling, Gaussian boson sampling, or standard boson sampling. That's discrete variables. That's what Quandela exploits. So this is true. We can use photon as photons and work in a subspace of the Hilbert space, which is a Fock space. And that can scale a number of parameters faster for the same number of photons. So this is some peculiar, interesting things, but it also allows to treat photons as qubits and convert any gate-based circuits into photonic implementation. And that's something that also Quandela provides in the full stack approach through its programming framework internally developed, which is called Perceval, that uses a graphical language in order to optimally transform any C-note or sequence of logic gates as we would implement in Qiskit, for example, into a compilation and a transpilation part that goes directly into the hardware platform that manipulates photons.
And if I compare your computer today to one in 2 years, for instance, is the number of qubits the measure that you're looking at, or is it something else? How do I compare photonic quantum computers?
Well, good point. Good point. If we look from the user perspective, what will change is surely the power and the spectrum of possible algorithms we can implement, both because it will depend, of course, on the number of qubits, but also on the encoding. If we look bottom up on the infrastructure, that will change a lot. In fact, internally, we are passing to the second generation of machines compared to what we are today. So we are moving from manipulation of single photons, where we are today, where we can find in a processor available on the cloud, to the manipulation of entangled photon directly. So the computing power will scale because the processing and manipulation part will manipulate directly entangled photon without the need to pre-entangle them and operate them. And that will increase dramatically the efficiency, reducing the number of resources needed in terms of hardware.
You mentioned a transpiler from gate-based applications to the photonic way of thinking, but if I want to focus and get the maximum out of the computer, do I program in gate-based mode, or should I think about the program in a different way?
Today, we are focusing with the partners, industrial partners we work on, in trying to bring out the power of the platform directly conceiving photonic algorithms. Certain gate-based algorithms can be hardly transferred into the photonic language, some other more efficiently, especially in machine learning based one, VQ, variational quantum type. That's because we can manipulate general phases on the circuits, and that's where we are looking at. And instead of trying to find a utility of these algorithms with today's platform or simulator, transferring a gate-based circuit into photonics, we take the orthogonal approach and look into classical algorithms, mapping them into photonic quantum algorithm. And this goes through mathematical problems that manipulates permanence, basically.
You have some computers already deployed, right?
Yes, indeed. Since a year ago, we have a Scala, which is a processor of 6 qubits available on the cloud, our proprietary cloud, and same time working through, of course, upgrading the platform on the cloud. We work also for providing on-premise machines to data center, to clients. And that's what we have been doing the past year, where we provided a machine to OVH Cloud, which is a cloud provider based in Europe.
What is involved in on-prem deployment? Do you need a dilution refrigerator? Do you need a lot of space or power supply? How does a deployment of an optical quantum computer look?
Today, the on-premise quantum computing machines we provide to customers, they are rack-based, the standard server tower rack, which makes them seamless, integratable in data center as they take the shape of standard CPUs or GPUs. they should not be seen as such, because indeed we use cryogenics. Cryogenics for the qubit generators and detectors that though work at 3 Kelvin, which is much, much higher temperature than superconducting qubits, which means that in terms of cryogenic technology, these are rack size cryostats and rack size air cooled compressors, which means that the entire machine and with compressor itself sits in the rack with a total power consumption below 3 kilowatt and the standard sockets in order to run it. This is the machines of today. While we will scale the number of qubits, we will multiply the number of these racks.
When you think about a 6 qubit machine, obviously there's learning that you can do with it, prepare for larger qubit machines with larger qubit counts. But is there something truly useful one could do with a 6 qubit machine? And I'm sure the same question could be asked about 16 or 26 qubits. But what are
Yes,
people doing with it?
today we try to, of course, have utility in the sense of scientific discovery, approximation of some algorithms, run toy models, of course. But one focus we had since the beginning was also related to cryptography. And that's what the first customer purchased the first machine for. Practically, the application that we run on this computer is to generate quantum certified random numbers. Something as Quantinuum and IBM have developed with their platform. What we have done is to develop the framework, theoretical framework, in order to use contextuality, so perform Bell inequality measurements on chip and still validate this theorem, and therefore extract quantum certified random numbers. And this is a simple application, but powerful itself. And we can even call it a quantum advantage, in the sense it's not quantum computing advantage, but it's a quantum advantage in cryptography, where quantum helps to increase the level of security compared to other classical methods.
You mentioned IBM and Quantinuum, and I think certainly IBM, when they think about larger number of qubits, they say at some point we're going to need to use interconnects. IonQ, I think the same thing. They have optical interconnects. Now, given that your system is optical from the get-go, how does it scale? Do you need multiple machines and somehow interconnect them, or you just add more fibers?
A bit of both. uh, as I was saying in the beginning, today we use semiconductor and let's call it matter-based qubit to generate light, to generate the qubit. So the light itself, so the qubits and parts of the computation, then gets out of the part of the machine and runs into fibers. So for us, qubits are already spread over different modules, which helps in the conception of the larger number of qubits machines, because for us it's updating, upgrading, and adding the number of modules. Of course, there is a lot of attention to be put into stabilization of the qubits through fiber and optimization of the optical links. But yes, this is indeed the approach, and we see it as a good way to start, because we bypass some issues that, of course, are related to manufacture large processor itself.
I believe you said you started the company in 2017, and maybe you were in quantum a little bit before that. So you're definitely an expert. What have you learned? What's new in the last 6 or 12 months that you didn't know prior to that?
uh, Well, clearly many things, but related to the business and technology, clearly that we should expect surprises coming along. Not scientific surprises because we know where we are going. Surprise in the sense of players or approaches that could disrupt both the market and the technology along the way. And this could be by emerging technologies, by changing materials, and therefore allowing to the use of more algorithms. So we are a bit of the idea that we do need to build quantum computers because if we put them there, someone will use them. So instead of just waiting to have the error corrected 1 million, 2 millions, 5 million quantum computer, we want to make the one in between because someone will use them. And what we see, some surprises could come up also from the user that will start to test also these intermediate machines.
You mentioned 1 million qubits, and that conjures some other optical company. Are all optical computers the same in terms of approach, or is there something substantially different between one optical manufacturer and another?
There are many differences. Uh, that's why also photonics has been for a while put aside because it's complex to understand and conceptually different and with many flavors. Just as an example, photonic quantum computers can use discrete variable, can use continuous variable. This is the main difference. If we scratch the surface, then we look directly into discrete variables, and there we can find different kinds of architecture. Some that are inspired by measurement-based quantum computing, which is different than gate-based ones. Some that uses different material, different technologies in order to generate qubits. As we do, for example, we use nanostructures, semiconductor quantum dots, while most of the other players uses nonlinear processes that occurs into silicon nitride, or other waveguides. So yes, there is an internal kind of creativity, let's say, in the photonic quantum computing company, and probably surprises will come also from emerging of different technologies and approaches.
When you install a system, I think you mentioned OVH as one of your first customers. Is the computer standalone, or is it used often together with classical compute resources?
So this one is standalone, but Perceval, the programming framework, has everything needed as APIs to be connected to the internal cloud, as for example of OVH, which is not opening this machine to their customer because it's used for internal research purposes. This means that we could directly connect Perceval to other machines, being GPUs or like Atos One simulator, and can be optimized so to run parts of the algorithms on those. And it's something we already do with the simulator. So the quantum simulator sharing part of the algorithm with the classical GPU. And we see this very important for the machine to come, and especially for the user perspective.
What is the limiting factor in scaling the machine? Is it laser power? Is it miniaturization? What would it take to take this machine and make it much, much, much larger?
The main engineering problem is losses, is the transparency of the elements is the capability to generate one qubit and make it pass through the entire chain of a system and modules and being detected. So what we call the entire losses threshold, this has to be very high in order for a certain number of qubits to reach threshold for error correction. And that's the hardest engineering problem all the companies are facing. Knowing that photonic qubits don't undergo decoherence itself, so the error is not the decoherence or phase flip or bit flip, etc., but losses. One photon is either there or not. And losing a photon is it's very easy, let's say. So in Quandela, what we say is every photon counts.
As we get close to the end of our conversation, I'm curious, professionally speaking, what keeps you up at night?
Many things. There are many nights a week, so I share the thoughts. It goes by period, and I would say engineering is, of course, the main one. How to allow the teams to get always the best providers, the best technologies, and to let the team do their research without caring about anything else. For example, recently we've been launching our own internal clean room to start developing all the fabrication process of most of the parts internally. And this, of course, has a lot of infrastructure, a lot of problems related to making this fast and transfer fabrications chain of production from one of the facility to another. This, of course, needs a lot of attention, and this is an example of the thing we were very careful in doing properly.
One thing I wanted to go back to, I think I understand the use in random number generation, but you mentioned machine learning. What makes photonic computers particularly useful for machine learning applications?
As I was mentioned before, the fact that machine learning allows the manipulation of large set of parameters, but not controlling each of the parameters. Also, the photonic approach allows to manipulate sets of qubits, manipulating the general phase, for example, without going into the control of each one. And there are many similarities also in the computer science term in this approach, from neuronal network to a large interferometer, which is the main manipulation object in the photonic circuits. And that's why we're trying to find smart way to map this kind of mathematical problem related to permutation and finding related one, similar one in standard computer science in some small or large set of problems can still impact industries.
And last, hypothetical, if you could have dinner with one of the quantum greats, dead or alive, who would that person be?
Oh, wow. Um, let's say Heisenberg.
And why?
Because there are, I think, many questions that I would ask on a general fundamental sense, which I couldn't find in many of his books.
Very good. Niccolo, thank you so much for joining me today.
Thank you, Yuval.